I'm going to talk for, say a few words about the electronic properties of Moire superlattice, which I've been working on for the last year or so with, together with colleagues at the University of Texas. And the Moire superlattices we have in mind, as you may know, are formed by, in van der Waals, two-dimensional materials, either by overlaying materials with a difference in lattice constant, or by twisting one material relative to the other, which makes a slow spatial variation in the stacking between the layers, and makes artificial crystals, since the electronic properties are insensitive to what's going on, that we'll be interested in are insensitive to what's going on the atomic length scale, and they only see this longer length scale Moire periodicity. Okay, so I know that I've prepared too much material, but the chair will stop me. I hope to say something about draw a line between the two different Moire superlattices people are studying most extensively now, which are transition metal dichalcogenides and graphene multilayers. And then I'll spend the rest of my time talking mostly about graphene multilayers, emphasizing two things. One, the fact that there's some generalized kind of magnetism all over the place in these materials, and also a few words about perhaps the big question, which is what's behind superconductivity in this system. So here's one contrast between graphene multilayers. This is actually twisted bilayer graphene and transition metal dichalcogenides. This subject started experimentally, as you all know, from the discovery of this phase diagram by Pablo Carrillo Herrero at MIT. This is actually data from Dmitry Yefetov at ICFO, but it shows resistance as a function of temperature with all this interesting structure, in particular superconducting regions, insulating regions, where you don't, in a single particle theory, expect insulating behavior. And it's characterized electrically, so resistively, by measuring resistance. And one of the very important aspects of this subject, of course, is that the period of these superlattices is in a range where it's easy to vary the number of electrons per period over all of the interesting range just with electrical gates. So you can dope without chemical doping, without introducing disorder. This slide emphasizes one important difference between graphene multilayers and transition metal dichalcogenide. It turns out it's harder to make good electrical contacts, and but it's in compensation, as God often compensates. It's easy to dig out a lot of interesting information optically, so these things are often probed optically. Experimental literature on twisted TMDs started with a series of preprints last fall, and I think there's all kinds of activity going on. So that is one way in which graphene multilayers are different from TMDs. I'm going to emphasize another way. And just to say what I'm going to say in the next few minutes, the electronic properties of transition metal dichalcogenide Moire superlattices are very much like those of two-dimensional atomic crystals. And they can be used to simulate lots of types of physics properties that we often ask about real crystals, like frustrated magnetism, Hubbard model physics, heavy fermion physics, and so on. On the other hand, graphene multilayers are quite different, quite special, and they simulate only themselves. So here's to explain why we have this difference. I'll start from the beginning. This is an electronic structure calculation for a single layer transition metal dichalcogenide. There's lots of interest in the properties of bosonic exciton systems in these Moire superlattices, but I'm going to talk only about the properties of electronic systems specifically holds in the valence band. And in this case, for a single 2D sheet, you can see that the top of the valence band occurs at the corners of the Brouin zone and at two inequivalent points in momentum space, which I'll refer to as valleys, related by time reversal symmetry, and that there's quite a substantial spin-orbit splitting between the two bands at the top of this. So mostly we'll be interested in physics on a length scale smaller than this spin-orbit splitting. And so there's only one spin state at each valley, and the lock spin valley degree of freedom acts like an effective spin. So it's a single layer as one band with a spin degree of freedom. Now here's a Moiré superlattice made by difference in twist angle or potentially difference in lattice constant. And because all of the physics we're interested in occurs near these Brouin zone corners, where we can approximate the effect of modulation by the Moiré pattern just by calculating the Hamiltonian and its dependence on stacking, which I call here D. Imagine rigidly moving one layer relative to another to vary the stacking. The dependence of the Hamiltonian on stacking, we only need to know it at the Brouin zone corners. And that's in this, since there's only one state there, this is just a number that has to be periodic when I move one lattice relative to the other by lattice constant. Of course, we can only get away with this kind of trick in semiconductors and semi-metals. But in the Moiré pattern, what happens then is that what the pattern acts is simply a periodic scalar potential that has the periodicity of the Moiré pattern. So the system we can realize is a 2D electron gas with a periodic sinusoidal, approximately periodic potential. As for example here, this is tungsten diselenide, molybdenum diselenide example. States we're interested in are at the top of the valence band, which turns out is in the tungsten. Those orbitals are d orbitals on the tungsten atoms, and the local energy goes up when they sit on top of a negatively charged ion. That's basically the physics of what produces this periodic potential, which has a typical size of around 50 millielectron volts. And in the Moiré pattern, simply by changing the twist angle, you can change the period of that periodic potential. You can't very easily change the strength of it, except by pressure, you can increase the strength. And so, for example, at 1.5 twist angle, you get one flat band, quite isolated from other bands. The electrons in this band are localized near the minimum of the potential for holes, which you can approximate by a harmonic oscillator. So this is basically a 1s harmonic oscillator level, and this looks very much like atomic physics. Of course, there are some important differences because the attractive potential is not a nuclear or ionic attractive potential. It's a periodic attractive potential, just a local minimum. So that does make some differences, but things are quite similar as, let's say, a cold atom system is. And by varying the twist angle, by varying the interaction strength, for example, by changing the distance to the gates, you can get into regimes. I think not all of this has been demonstrated yet. I think people are seeing basically Hubbard physics, but I expect people will be able to see heavy fermion physics, frustrated magnetism, and many other things that are of interest in the system. Let's contrast that with what I'm going to concentrate on for the rest of my talk, which is graphene bilayers. This is a single graphene bilayer. In this case, the low energy states are carbon pi orbitals, again, near the Brouin zone corners, but there are two states, as you can see here. because of the two sublattices of graphene's honeycomb lattice. So there's a sublattice degree of freedom in this system, and not apparent here. Each of these states in single layer graphene has a spin degeneracy and also has a degeneracy between these two valleys. So there are actually 8 low energy bands. So that's a big difference already. We can go through the same kind of argument to build a model of the low energy electronic structure. In this case, there's a slight twist because if I translate, for example, the top graphene layer relative to the bottom graphene layer by 1 lattice constant, turns out that the dominant way in which the 2 layers modulate each other is by electrons tunneling back and forth. And it turns out because of that, when you translate by a lattice constant or by 1 period of the Moiré pattern in the Moiré pattern, then you get a phase factor in the tunneling Hamiltonian, which is easy to accommodate. And when we followed this recipe a number of years ago together with Rafi Bistritzer, we got the surprise that we didn't anticipate that unlike the TMD case in which the bands just get narrower and narrower as you make the lattice constant bigger and bigger, in this case, the bands get flat at certain set of discrete twist angles, and then they get broad again, and then they get flat, and then they get broad as a result of an interference basically between the tunneling back and forth between the layers and the tunneling between sublattices within a layer, which is responsible for the Dirac dispersion. Yeah, so there's nothing like an atomic orbital in this system. So let's see how far I get. But here are some of the main experimental facts of twisted bilayer graphene, which is all I'm going to talk about. The insulating states are common when the number of electrons per Moiré period is an integer. The insulators are sometimes Chern insulators. I'm not going to be able to talk about that in any length. I'm not sure if you are, David. Are you?
No, I'm talking about something.
Okay. Anyway, these twisted bilayer graphene is now our best experimental example of a quantum anomalous Hall effect, something discovered initially by David about a year ago, I guess. Superconductivity is all over the place and common when we're in the metallic regime, non-integer filling factors. And interestingly, the resistivity, when we're close to these magic angles where all this strong correlation of physics occurs, has surprisingly strong temperature dependence at low temperature. Okay, so I'm going to say a couple of things, couple of reasons why it's really very challenging and an incomplete task to understand the properties of twisted bilayer graphene. I think we're making progress on this, but I'll mention some of the complications. What this slide emphasizes is the basic energy scale of interlayer tunneling in bilayer graphene is 300 millielectron volts. When the bands get narrow at this magic twist angle around 1 degree, they narrow to, let's say, 5 millielectron volts. So they're narrow by a factor of, let's say, almost 100. So what's left over after they get narrow depends on a lot of details. And so, for example, this is one detail that was left out in our original work on this. And that is, let's just mention the simplest idea, which is corrugation. So it turns out these graphene sheets are most stable with a certain type of stacking, AB stacking. So the layers end up being closer together when they locally have AB stacking, and that makes the tunneling between the layers stronger in the AB regions of the crystal. and that changes the shape of the periodic potential or the periodic tunneling between the two layers, which defines the Moiré pattern. And in particular, there are two parameters that appear in most models, and A and B in this expression are dimensionless versions of these two parameters. They're just tunneling between the same sublattice, AA tunneling, and tunneling between different sublattices, AB tunneling. And so it turns out that at the center of the Brouin zone, I'll be showing a lot of in a minute, when you get in twisted bilayer graphene, the center, the gamma point of this Brouin zone, that's where the electrons come from furthest apart, from 300 millivolts away as a function of twist angle, to become nearly degenerate near the Dirac point. And it turns out that it depends on details, on the ratio of AA to AB tunneling, whether when these bands come together, they come together as doubly degenerate pairs, which would mean that there's no energy separation between the flat band and the remote band, so-called, at the gamma point, or they can come together as singly degenerate levels. So the character of the wave functions near the gamma point, the character of the wave functions near the gamma point and is very sensitive to details and very different from other points of the Brouin zone. I'm going to have to go faster now. Also, it turns out that the shape of the bands, even when you don't include quantum fluctuations within the flat band, the shape of the flat band depends a lot on the strength of interactions, and because of exchange interactions with the negative energy C. And that's an unusual feature connected to my next point, which is that the wave functions in these graphene multilayer systems, even without the Moiré modulation, are very sensitive to wave vector. This is a plot by plotting the bilayer state as a function of momentum in some block sphere representation at the quadratic band touching point of bilayer graphene. The wave functions very, very rapidly, and it turns out exchange interactions want to heal that by basically making a vortex core in this structure, and that opens up a gap. So this is well-known physics in bilayer graphene, leads to a spin density wave state. And the the basic lesson is I'm going to make a couple of points about mean field theory calculations, which you can read as basically the DFT calculations of this subject. But when you do DFT, it's absolutely essential that you include the full non-locality of exchange, or you'll get it completely wrong. And yeah, so in magic angle twisted bilayer graphene, this is mean field calculation as a function of twist angle interaction strength. And what it shows is that as you go towards the magic angle, the bands get very flat. You tend to open up a gap in neutral bilayer graphene, which is very similar to the one in character, the ones already known in just ordinary bilayer graphene. And it's occurring because the bands are getting very, very flat, enhancing the role of interaction. So understanding a gap at neutrality then is not a surprise. It's the gap at the other integer filling factors, which are were really a surprise. And I think now it's quite clear that we know that this is some kind of insulating magnetic state, analogous to an AL state of an antiferromagnet, if you like, except that you have, instead of having spin, you have spin and valley. Turns out the valley polarization is what is combined with that topological structure in the band structure is what is responsible for the quantum anomalous Hall effect. And so having those splittings between the bands, like spin splitting in a Néel system, if you like, is something that you can only happen if the bands are flat enough compared to the strengths of the interactions. And so you can estimate that this occurs over some range of interaction angle, actually where this black line is positive. And so all of that stuff seems to be pretty well understood. I have to skip about the quantum anomalous Hall effect. But the important point is that these broken flavor symmetries, spin valley flavors, it seems quite clear that they occur through most of the metallic regime, most of the non-integer filling factor regime, which of course what we can explore with doping. Mean field theory calculation should expect, says that the broken flavor symmetries that occur in insulating cases should occur also at over much of the metallic regime. And actually, this is an example of Shubnikov to Haas measurements in magic angle twisted bilayer graphene by Matt Yankovitz et al. And this is basically showing that there's a Fermi surface, these magnetic oscillations and resistivity. And if you look at the degeneracy of the Fermi surface here, you can see that there are 4 degenerate Fermi surfaces here, 2 degenerate Fermi surfaces. And so this is, I think, quite well established theoretically and, I'm sorry, experimentally, and expected theoretically, and maybe the superconductivity seems to occur in broken symmetry states very often. I'm going to run out of time, but let me just tell you, it would be wonderful to have photo emission in the system. Dan, can you arrange that? Because we have no idea what the Fermi surface looks like in the metallic state. For all of the reasons I said at the beginning, our complications and all of this interaction dressing of the states really changes the Fermi surface in a way we don't have, we cannot guess at. And here's a substitute, the Hall density. The Hall density naively measures, the size of the Fermi surface, whether it's electron-like or hole-like. And this is a typical Hall density by Sato et al. In Andrea Young's group, I believe. And the interpretation of this is that starting from neutrality, going to the whole side, you have a nice, fairly symmetric Fermi surface. And probably what's going on here is that you break flavor symmetries. So you only go from 4 Fermi surfaces to 2 Fermi surfaces and have a hole-like Fermi surface. So it seems like the hole-like Fermi surfaces at negative filling factors and electron-like Fermi surfaces at positive filling factors, and this is where superconductivity occurs for the most part, are perhaps fairly dispersive, because you can see the Shubnikov to Haas, and fairly symmetric. If you compare that with, here's a actual calculation for the non-interacting model of magic angle twisted bilayer graphene as a function of, this is hole filling, and the Hall density calculated using the correct formulas from Boltzmann transport theory don't match the hole density, and the jump from hole-like Hall density to electron-like Hall density occurs very far away from the middle of the band. Okay, 2 minutes. And we can sort of understand that. So, okay, I have 2 minutes left. I'm just going to try and get one idea across. Here's a calculation for an insulating state. I think it might not be very different for a metallic state of collective excitations in this system. So this is an insulating state. This is actually an insulating state. Would be an example of a quantum anomalous Hall state with 1 valley filled for 1 spin. So there are a bunch of collective modes actually corresponding to transitions between the occupied states and all of the empty states. And the very surprising thing about this, I'm not showing you here the band excitations in this insulating state, which have an energy of about 12 MeV. These are only collective modes. And there's this branch of collective modes that exists throughout the Brouin zone, which corresponds to basically, for the excitation spectrum, to having a local degree of freedom on every lattice site. And so it acts like it has a local electric degree of freedom on every lattice site. It's happy to be in any spin valley state and in either band, doesn't care much which band it's in. It costs very little excitation energy to make these collective modes. And I think that, so this is something we can discuss online since I'm going to run out of time. The final things I'm going to say is the very temperature-dependent resistivity in twisted bilayer graphene that's seen only at magic angles. I'm very highly suspicious that this is the origin of them because no other explanation works. And I'm going to, here's when you come to superconductivity, here's a straw man for superconductivity in twisted bilayer graphene. You could imagine the possibility it's mediated by these optical phonons. That's like the superconductivity in intercalated graphite is basically mediated by interactions with these phonons. And you can imagine if you get the high density of states, that can happen here as well. But the competition with Coulomb interactions, which we've looked at quite a lot, it's quite hard to imagine that the Coulomb interaction can be made weaker than these essentially instantaneous optical phonon mediated interaction. And instead that these, I think these collective modes that exist, I believe, in the metallic state as well, as evidenced by the linear and T resistivity, are a very strong candidate for superconductivity. So let me stop there and leave you with that. So thank you very much.
Thank you all. We have like 2 minutes for questions, either from the audience or from the remote audience. Yes.
So maybe I missed that, but the reason for the smallness of these excitation energies, right? Some of them seem to be going to nearly zero near the gamma point. So this is proximity to these symmetry breaking states?
Yeah, so
excuse me, can you repeat the
question? So the question is, what is the reason for the smallness of the collective excitation? And that some of the collective excitations seem to go to zero energy at gamma, at zero wave vector. Yeah, so the, one of the symmetries that's broken in these broken symmetry states is spin rotational invariance. So there is a spin Goldstone mode. Before we did these calculations, we weren't really certain that the spin wave would be below the interband particle hole continuum throughout the Brouin zone. It is. But what was really surprising to us in these calculations is that the interband excitations between the occupied flat valence band and the empty flat conduction band without any spin or valley flips, that collective mode also, there is also collective mode in that branch, which is below the particle hole continuum throughout the Brouin zone, as though an electron sitting on that site in this insulating state is happy to be in the valence band or the conduction band. It only costs a little bit of energy to change the local state of the system. Seems to have, one state for every Q means one state for every site locally. Even though we don't, as you may know, really know how to make linear functions in this case. It seems like the collective modes don't care about that very much.
Okay, one more question, I would say. Martos.
So if you doubt that the phonons are responsible for or the classical picture for the superconductivities, it's not valid. What would be your take on which bosonic glue might do the important job here?
Yeah, so
Can you repeat the question?
yes, thank you. So if the question was, if indeed phonons are not responsible for superconductivity, what kind of bosonic glue do you think could be responsible? And yeah, so I'm certainly not dogmatic about any of this at this stage. I mentioned the optical phonons. The optical phonons, you know, the phonon energy is many times the bandwidth. So those interactions have to be considered as instantaneous attractive interactions, which have to be paired with the instantaneous repulsive Coulomb interactions. And in the slides I went through very rapidly, we look carefully at whether that leaves any channel, you know, SD, those words are not really important, but the equivalent of that, in which you could get superconductivity due to these instantaneous interactions. And the answer is, it's a little hard to be sure. But I was proposing at the end that these collective modes, multi-branch set of collective modes that appear in calculations we've done recently are a candidate for being responsible for the linear T resistivity. And it's a good thing to, I mean, it seems quite plausible to expect that whatever is responsible for the linear T resistivity could be responsible for the superconductivity. And time for me to get off the stage.
Yes, thank you. Bear in mind, we do have half an hour for discussion after the next talk,
Yeah.
which is Philip.
Which is going to be 20 minutes, but because I think we should go back on schedule. But let's
Yeah.
thank Allan again.